Okay, second topic is about the computation space. The most fundamental question about the robot. Where is it? Okay, the answer is given by the robot configuration. Okay, robot configuration is about the specification of the position, all the point of the robot. Actually, let's consider the wall doors attached to the wall like this. Using the hinge joint will make some rotational motion. So the configuration of the door can be represented by a single number, the angle set about each hinge. Okay, let's consider the point in the plane. Here, in order to specify the position of the point, we need two variables such as the x and y coordinate. Okay, let's consider the coin lying head up on the flat table. This is a rigid body, not a point. Okay, in order to explain the position of inside the rigid body, okay, let's take some point. This will require x and y position coordinate. And then, in order to describe the orientation of the rigid body, some angle should be specified. Okay, the configuration of a coin lying head up on a flat table can be described by the three coordinate. Two coordinate about the location of a particular point of the coin. The one coordinate theta for the coin's orientation. Okay, the number of the degree of freedom of the robot is the smallest number of the real valued coordinate needed to represent each configuration. Okay, let's consider the previous example. The door has 1 degree of freedom. The point on the plane requires has the 2 degree of freedom. Coin lying lying head up on the flat table has a 3 degree of freedom. If you extend the head up and the tails up case, forward and backward side, then the one more discrete event is required. Head up, what tails down, tails up. In this case, 4 degree of freedoms. Okay, let's consider definition of the configuration. Configuration of the robot is a complete specification of the position every point of the robot. That is the formal definition of configuration. The minimum number of the real valued coordinate needed to represent the configuration is the number of degree of freedom of the robot. The minimum number of real valued coordinate is the degree of freedom to describe the configuration of the robot. Okay, n-dimensional robot, n-dimensional space containing all possible configuration of the robot is called as configuration space. In other words, C space. This space implies n-dimensional space containing all possible robotic configuration. Okay, configuration of the robot is represented by a point in C space. Okay, later we will deal with this terminology. Anyway, the task space means C space of the robot's end effector. Okay, the section 2.1, the degree of freedom of the rigid body. After that, we will deal with the degree of freedom of the robot. And then we will take some last. Okay. Okay, let's see the figure A. In here, in order to specify the rigid body motion, okay, rigid body posture, let's take some point A. This will be determined by using the x and y coordinate. And then let's just specify the one more point, B. Okay, maybe the B point is obtained by using the some circle about the point A. Okay, so the distance or radius will be the same at any point, and in order to specify the point B, the angle theta will be required. In other words, the B requires just 1 degree of freedom because it has the one constraint. So the constraint DAB restricts the choice of the B point to those points on the circle of the radius DAB centered at A. In other words, the angle pi AB can be introduced by to express the point B with the x-axis, 1 degree of freedom. That means A requires 2 degrees of freedom, B requires 1 degree of freedom. Let's add the one more point, C. It has the two variables, such as the xc and yc, but it requires two constraints. So there is no degree of freedom, 0 degree of freedom. It means in the planar space, in the planar case, the 3 degree of freedom is enough to describe the rigid body motion. On the other hand, the special rigid body has 6 degree of freedom. Okay, let's come back to the previous example. Okay, in the special case like this, x and y and g coordinate will be specified. Let's choose a point. It will require x and y, x, y, g coordinates requires 3 variables. Let's choose the B point. The B point has the 3 variables, but it has one constraint, so 2 degree of freedom will be enough. And then the C point can be chosen at any point inside the coin. It also has the 3 variables, but 2 constraints should be used to describe this point. So 3 minus 2, just 1 degree of freedom remains. It means 3, 2, 1 degree of freedom is enough to describe the rigid body motion in the special case. Okay, so the once A position is specified, 3 degree of freedom, and the constant DAB restricts the choice of the B point to those points on the sphere of radius DAB centered at A. In other words, latitude and longitude can be introduced to express the point B on the sphere, so it means the 2 degree of freedom because of the one constraint. Once we have chosen the location of the point B, the constraint DAC and DBC restrict choice of the C point as one point in the intersection circle. It means 1 degree of freedom is remained. So just 6 degree of freedom in the case of the special rigid body case. The general rule for determining the number of the degree of freedom of the system, okay, sum of the freedom of point minus number of the independent constraint. Okay, we have talked about this formula. It can be interpreted as the second equation. Sum of the variable minus sum of the independent equation is the same. Sum of the freedom of the body minus number of the independent constraint. Actually, like this, we can calculate the degree of freedom. Okay. The second topic, the section 2.2, degree of freedom of the robot. Okay, consider example of coin, example of the door. Okay, in the case of the door, the without hinge joint, door is the rigid body, and it has the 6 degree of freedom because each motion will be dependent on the three-dimensional space. Okay, it means the door is attached to the wall. At that time, hinge joint just provide 1 degree of freedom. It means the hinge joint will provide five constraints to make a limitation of the motion. Okay, the door connected to the wall by the hinge joint has 1 degree of freedom by imposing the 5 independent constraints. Okay. Okay, so the door's C space is represented by some range of in the interval over which theta is allowed to vary. Okay, because it must be the one-dimensional space. Okay, the joint constrain the motion of the rigid body, so the reducing it reduce the overall degree of freedom. This kind of observation will suggest some formula for determining the number of degree of freedom of the robot. Okay, the Grubler formula is very well known there. Okay. Before explaining the Grubler formula, we will introduce some robot joint, 6 kinds of robot joint. As you can see here, the level joint, it has the nickname of the hinge joint. Okay, it will be denoted by the R, capital R. It allows rotational motion about the joint axis. It has 1 degree of freedom, like this. Okay, the prismatic joint P, denoted by the P, it has the nickname of the sliding joint or linear joint. It allows the translational or rectilinear motion along the direction of the joint axis, like this. Okay, the helical joint, denoted by the H, it has the nickname of the screw joint. It allows the simultaneous rotation and the translation about the screw axis. The translation is dependent on the rotation, so it just provides 1 degree of freedom. Okay, like this. By rotating motion will generate a linear motion of downside or upside. Okay, cylindrical joint, denoted by the C, like this, will allow independent translation and rotation about a single fixed joint axis. It has 2 degree of freedom. Rotation is possible, translation is independently possible. And the universal joint, denoted by the U, it allows 2 orthogonal rotational motion, like this. Okay, so we can get 2 kinds of rotational motion. So it provides 2 degree of freedom. Okay, the special spherical joint, denoted by the S, it has nickname of the ball socket joint. Okay, it provides 3 kinds of rotational motion. It functions much like our shoulder joint. Okay, so it has 3 degree of freedom. Okay, joint providing the freedom to allow the one rigid body to move relative to another. On the other hand, joint provide constraint on the path of motion of the 2 rigid body it connects. Okay, let's consider the level joint. It allows 1 freedom of motion between the rigid body in space. On the other hand, it provides 5 constraints on the motion of 1 rigid body relative to the other. Okay, in the case of the planar, the level joint will provide 1 motion freedom and 2 constraints. Okay, generalizing the number of the degree of freedom provided by the joint must equal. Okay, in the case, okay, the number of the degree of freedom will be obtained. In the case of the planar, 3 should be used. In the case of the special, 6 should be used. Okay, this terms minus the number of the constraint will be the motion degree of freedom of the joint. Okay, the freedom and the constraint provided by various joint is listed like this. In the case of the relative joint, level joint and the prismatic joint can be used for the planar and the special case. So it has 1 degree of freedom, but in the case of the planar, it has the 2 constraint. In the case of the special, it provides the 5 constraint. The remaining 4 joint can be used for only for the special mechanism. So helical joint has the 1 degree of freedom and the 5 constraint. Cylindrical joint has the 2 degree of freedom and the 4 constraint. Universal joint 2 and 4. Spherical joint has the 3 degree of freedom and the 3 constraint. Okay, this is the main topic of section 2.2, Grubler formula to determine the how to count the degree of freedom of the robot mechanism. Okay, consider the mechanism consisting of n link. Link will be denoted by the n, the number of the link. Well, we should notice that the ground is considered as a link. You should mark in mind. Ground should be considered as a link. Let J is the number of the joint. M is the number of the degree of freedom of rigid body. It means M can be 3 for the planar. M can be 6 for special mechanisms. Fy is the number of the freedom provided by the joint. Ci, number of the constraint. It means number of the freedom plus number of the constraint will be the M. In some case 3, some case 6. Then Grubler formula for the number of the degree of freedom of the robot is obtained. And n minus 1 minus sum of all the joint constraint. Okay, the joint constraint Ci can be replaced m minus Fy. The summation implies the m appears j times, so mj will go outside. So j is appears, and the remaining term is sum of the motion freedom of a joint. Okay, we will use the last equation for determining the degree of freedom of the robot. Okay, we have the 2 comment for the Grubler formula. Okay, it is noted that this formula holds only if all joint constraints are independent. Some joint constraint is dependent. At the time, this formula is not effective. If they are not independent, in that case, this formula, the Grubler formula, provides lower bound on the number of degree of freedom. It means the actual degree of freedom will be larger than or equal to the Grubler formula result, because it provides lower limit of the degree of freedom. Okay, we will take the several example. The first example is about the Popper linkage. And the second one is the slide crank mechanism. Okay, let me calculate. Let me apply the Grubler formula. Okay, let's count. The ground is first link, and link 2, link 3, and link 4. Let's count the joint. 1, 2, 3, 4. So it means n is 4, the number of link. J is 4. So let's apply the Grubler formula. Okay, so this is 4. It must be the planar mechanism. So m is 3, minus 1 is 4. So all the joint has the 1 degree of freedom. So 4 times 1. It means we have 1. The Popper linkage has the 1 degree of freedom. It's very straightforward to obtain the degree of freedom of the mechanism. Okay, let's consider another example, slide crank mechanism. Okay, in here, let's count the link. The ground is 1, 2, 3, and then this part is 4. How about the joint? N must be the 4. Let's count the joint. 1, 2, 3, 4. So joint is 4. Okay, and then the 3 revolute joint will be the 1. Okay, the prismatic joint will be the 1. So this is not 3, it's 4, because the 1, 2, 3, 4. So we have the same result. So the slide crank mechanism will have 1 degree of freedom. Okay, let's apply another concept to calculate the degree of freedom. Okay, let's combine the 2 joints. It has the level joint and the prismatic joint. Let's combine it as a PR joint. It's a new type, prismatic and the level joint. It has 2 degrees of freedom provided by the joint. Okay, in this case, let's count link 1, 2, 3. That's all. The number of link is 3. Let's let's count the joint 1, 2, 3. PR joint. So joint is the 3. But F1 is the 1 because the level F2 is the 1. But F2 is 1. F3, PR joint is the 2. Okay, let's apply this data like this. Then we have the 1. It means some joint can be combined to make the new type of joint, but it does not affect the result of the Grubler formula. Okay. Let's read the last sentence. The mechanism consists of the 2 R joint and 1 RP joint or PR joint. Concatenation of levolute and prismatic joint. It was combined so that Fy is 2. And the 3 link and 3 joint and 3 link and 3 joint, and the degree of the freedom of some of the freedom of each joint will be the 4. 1 plus 1 plus 2. Okay. Let's apply the Grubler formula. Okay, number link 1, link 2, link 3, link 4, link 5. So n must be the 5. How about joint? 1, 2, 3, 4. Joint is 4. Okay, so let's apply the Grubler formula like this. And then this is the 4. 3 times 5 minus 1 minus 4 plus 4. So it has 4. Like this, this 4 link mechanism has the 4 degree of freedom. Okay, the end point is attached to the ground like this. At the time, we have the closure. It is not open chain, it is closed chain. Okay, let's count the number of the link. 1, 2, 3, 4, 5. So number of the link is the 5. And how about the joint? The number of joint. 1, 2, 3, 4, 5. This is also 5. Every joint provides 1 degree of freedom. Okay, so the DOF is the 3 times 5 minus 1 minus 5 plus 5. Okay, it provides 2. It means the 5 link mechanism, 5 mechanism will have 2 degree of freedom. Okay, It's correct answer. Okay, this kind of mechanism is called as Stephenson's six-bar linkage. Okay, let's count the number of the link. 1, 2, 3, 4, 5, 6. N must be the 6. How about joint? 1, 2, 3, 4, 5, 6, 7. J is the 7. All the joint has the 1 degree freedom. Okay, so DOF is equal to 6 minus 1 minus 7 plus 7. Yes, this is planar, so 3 times. Okay, it means 1. It has 1 degree of freedom. Okay, what the 6-bar linkage? Let's count the link. And 1, 2, 3, 4, 5, 6. Okay, 6. Joint 1, 2, 3, 4, 5, 6, 7. 7. All the joint has the 1 degree of freedom. So we have the degree of freedom as a 1. Okay? You can check the result. Okay. This example is about overlapping joint. Okay. Everything's the same, but let's think of this joint. Actually, joint connect the 2 rigid body, other joints to 2 rigid body, but this joint has the 3 rigid body. It makes some problem. So the joint is, let's assume that joint is stacked. 2 joint is stacked to connect 3 joint, 3 link. Okay. Okay. Let's count. It has the 2 level joint is here to connect 3 rigid body. Okay. Let's count N. 1, 2, 3, 4, 5, 6, 7, 8. 8 joint. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 9. All the joint has the 1 degree of freedom. So DOF 3 times 8 minus 1 minus 9 plus 9. It implies 2. I'm sorry, the 3? 3. Okay. Like this, 3. So this mechanism has the 3 degree of freedom. In here, so we should notice that the overlapping joint should be counted. Should be counted in the J. Okay. Apparently, it has 1, 2, 3, 4, 5, 6, 7, 8. It's long. The 3 link is combined with each other. At that time, 2 overlapping joint appears. Okay, appear. Okay. Okay, take another example. It's about the redundant constraint and the singularity. Okay, the first one is called as a parallelogram linkage. Okay, let's count 1, 2, 3, 4, 5. So number of the link is the 5. How about joint? Joint is the 6. Okay, if you apply this data to the Grubler formula, will result in zeros. It means this is a rigid structure. Is it right? This structure does not move anymore. I don't think so. This linkage can move with each other, such as some rotational motion will be possible like this. Is it right? So there is some problem. What the problem is? In here, the constraint is not independent. Okay, let's consider the okay. If we remove this link, how about that? The same motion appears. In this case, this linkage does not provide any independent constraint. It means it's dependent constraint. So in this case, we can remove this part. Let's count. Okay, and about I'm sorry. The N is the 1, 2, 3, 4. J is the 1, 2, 3, 4. It will provide 1 degree of freedom. It's correct answer. As mentioned before, constraint should be independent. Okay. One more, the Grubler formula provides the lower bound on the degree of freedom only if the constraints are independent. Okay. So some case we can get the 0 or minus 0 degree of freedom, but the actual mechanism is movable. At the time, we should count the dependent constraint exist. Okay. Let's move to the next example. Singularity. I'm sorry, the singularity. Okay. It must be the fiber linkage. As mentioned before, fiber linkage has 2 degrees of freedom, but the first and the last link has some fixed angle. At the time, this kind of posture will be maintained. Okay, it does not have any degree of freedom. It looks like the structure. This kind of phenomenon will be called as singularity. Okay, so there is singularity over there. Sorry, there is no singularity here. On the other hand, the first and the last link has linearly aligned like this, and the second and the third link is overlapped each other. Then, without any motion of the first and the last link, the rotational motion will be possible internal way. This kind of phenomenon is called as a singularity. Okay, I have talked about the 2 kinds of singularity: structure and 1 degree of freedom internal motion. Okay, this is also the important topic in the kinematics later. Okay, let's count the degree of freedom of delta robot. Delta robot is very famous. This is fixed base. This is the movable base. Okay, let's count the one leg. Let's consider one leg. The link. Let's count the linkage. 1, 2, 3, 4, 5. Okay, the linkage number of the link will be 3 times 5 plus fixed plus movable plate. So 17. Let's count joint. 1, 2, 3, 1. I'm sorry. 1, 2, 3, 4, 5, 6. 6. Is it right? I'm sorry. Then one more. 1, 2, 3, 4, 5, 6, 7. Okay, joint 3 times 7. 21. Okay, let's apply the data. This is the 17. This is 21. All the joint we have the 1, 2, 3R and the 4S. 3R and the 4S. This robot system has the 3 legs. So we have the 9R, 12, 3. So we have the 15. Is it correct answer to describe the degree of freedom of this delta robot? Is it right? That's right, because it has the 12 internal motion. Let's explain it. Okay, the spherical. This is the spherical. This is another spherical. If it is connected using some rigid body, actually it can be rotated along the longitudinal axis. Is it right? This kind of motion is possible between the spherical and the spherical joint. So in here, it has one internal motion. It has another, and another. So this parallelogram has the 4 internal motion 3 times. So minus 12 is required to remove the internal motion. So we have the 3 beats of motion of end effector part. Okay, of this 15 degree of freedom, only 3 are visible at the end effector because it has 12 internal degree of freedom. Okay, let's move to next example. Okay, let's consider student platform is here. Student platform leg, okay, prismatic and universal joint and spherical joint, spherical, universal, and this is prismatic. So UPS joint is used for each leg. Okay, so this is written in here. Let's count the rigid body. Each leg has the 2 legs, 1, 2, 6 times, 12, 13, and 14. So n must be the 14. Okay, let's count the joint. 1, 2, 3, 6 times. So it has 18. 6 times 3, it will provide 18. Okay, this is 14. This is m is 6. Joint is 18. Okay, the 6 times of universal the revolute prismatic, 6 times universal, 6 times spherical. So the result will be the 6. Okay, so on the fixed base plane, the movable plane will produce the 3 kinds of translational motion and the 3 kinds of rotational motion. Okay. Okay. One more. If you change the U into the S, this is the S, this is the P. SPS leg will be possible. In this case, we will get 12. Why do we have the 12? It depends on the 6 internal motion. Okay. Between the spherical and the spherical, we have the internal motion. It does not affect the end effector of this robot system.